Sam here, some of you may have picked up this Sam.
下来手上吃个傻锅。
Yes, we'll get regrade wouldn't happen until after Thursday. The instructors are getting together on Thursday to do the regrade, but we wouldn't know about them until Thursday. What do you say again? You go to any parties? Oh, no. I don't have time to No, actually, this is unofficial, but it's really bad for students, I think.
You got the party while you're still young.
When you go for those unofficials,
Yeah, what do you do for unofficials?
The liquor store makes money off the bar makes money off. But you're very gung ho for unofficial. So you're back. You're Ramesh, right?
Yeah.
And what's his name again?
Update.
Update?
Avi.
Arby. Okay. Try to remember that. Haven't seen you for a while. Are you sitting in the back?
Yes. Sometimes you don't get.
Oh, okay.
Oh, shit.
I didn't hear it.
Okay, you won't get your regrades back until after Thursday. Okay, and I still have your old exams here, if you want them back. And today we're going to talk about chapter 4.4, resonances. Okay, 4.4. Resonances. What are resonances? You probably have encountered that before in another course. Did you talk about that in 110? No? Did you talk about that in your physics course? You did, right? So I give you a very simple example of resonance, which is that if you have a capacitor, and you may have that hooked together with an inductor, this thing can exchange energy. What you have here is actually electric field stored energy in the electric field, and as the current flows in this, there will be magnetic field energy stored here. Okay, E field, and both those kinds of fields store energy. And when they exchange energy back and forth between them as the current flows between them, you get a resonance situation when you have an exchange of energy. I do a very simple demo here. This is another physics problem where you see resonances. You probably have come across this device before. And if I let it swing, it goes by itself. Okay? You probably have seen this in the physics course, right? And there is an exchange of two kinds of energy in this resonance situation. What are the two kinds of energies that you can identify? Yes?
Potential and kinetic.
Very good. Potential and kinetic energy. Okay? As you move this thing up, it gains potential energy. As it moves from the high to the lower point, it gives up potential energy. Potential energy is converted into kinetic energy. Okay, so you can see this, right? So the same thing happens. As this thing resonates, it exchanges the B field energy with the E field energy, and you have a resonating system. Let's see how the mathematics of this works. Okay? So, if I have a resistor together with a capacitor, then I can write down the phasor circuit equation if I want to. And that phasor circuit equation is just that the impedances times the current that flows, Okay, the current, this impedance is just 1 over j omega c. These are the impedances R. The impedances times the current that flows, but the current that flows gives rise to a voltage drop that adds up to 0. Okay, this is actually V. This is Z times I. Okay? This problem has no solution unless omega is a complex number. Okay? So the textbook says that if omega is pure real, you cannot have a solution. Because if omega is pure real, then this part is pure imaginary and this part is pure real. There's no way that this equation is satisfied unless I is equal to 0 if omega is pure real. Okay, this is something that you have to keep in mind. Okay, because you might be misguided in the future that it's not true that this problem has no solution. This problem does have a non-trivial solution if z equal to 0. But z cannot be equal to 0 unless omega is constant. Okay, so according to what the textbook teaches you, that I has to be 0 if omega is pure real. Okay, and then you have the other situation where you have an inductor together with a capacitor, and then the impedance will be j omega L for this one, it will be 1 over j omega C for that one. And if you set up Kirchhoff voltage law for this problem now, you get j omega L times I, if there's an I that flows, plus 1 over j omega C times I, and that must add up to the voltage in the loop, but there's no source in the loop, so it adds up to 0. Okay? So again, you get a very similar equation like before. I equal to 0, and you're lucky with this problem. Even if omega is real, a solution can exist. Okay, say if I assume that omega is real, then if I multiply this out, I get that this must be equal to that. Okay, if omega is real, then I have the requirement that this must be true. In order for this thing to be 0, this part is z. Okay. If z is equal to 0, then I need not be 0. Okay, I is not equal to 0. So if I can set the impedance to 0 value, then I does not have to be 0, which means that there is a current that can flow in this circuit despite the fact that there's no source driving it. So if you work this out, it says that 1, if I multiply this by j omega c, throughout on the left I get 1, on the right I will get omega square LC. Okay, if I just multiply this equation all the way through by j omega c, I get 1 equals to omega square times LC. And then it tells me that if omega equals to 1 over square root of LC, okay, a solution can exist. A solution where I is not equal to 0 can exist. Okay, there will be no contradiction. If this term goes to 0, I can be non-zero. So this frequency is also called a resonant frequency. So this is the mathematics of it. But what actually is happening physically? What actually is happening physically is, as I said before, it's like the pendulum that I showed you. Okay, there is an exchange of electric energy stored and magnetic energy stored back and forth between these two systems, and the system can sustain itself with the current flowing even though there's no external driving source. Okay, everybody understands that and what this means, and this can only happen at the resonant frequency of the circuit. This is called the resonant frequency. Okay? Any questions so far? So if you look at the current, if you're curious, you can look at the current will be 90 degrees out of phase with respect to each other. Okay? The current and the voltage will be 90 degrees out of phase with respect to each other. If I call this current, and then there's a voltage V, across the two circuits and the two devices, then you can say that IT must be equal to real of I e to j omega t. And then Vt, the voltage that is in the time domain that corresponds to that phasor of voltage, is real of V e to the j omega t. And if we assume that I is equal to I magnitude e to the j theta, okay, then you can see that V has to be equal to just I times the impedance, okay. It can be this impedance or the negative of the other impedance depending on where you want to define the current to be. So I define V to be I times this impedance, then V will be just I times 1 over j omega c. Okay, this is the impedance that the I sees, so V must be equal to that. And hence you have V must be equal to I over omega c e to the j theta minus pi over 2. There is a 90-degree phase shift. As I move this j to the numerator, it becomes a minus j, and then move it to the exponent, it becomes e to the minus j pi over 2. So what I have done actually is to replace this with minus j, to replace it with minus j pi over 2. And then lump it together with the phase that comes from I, and then the exponential phase will have this factor over here. Then you can convert things to the time domain. Okay, IT would be equal to, if I plug this in there, the magnitude of I cosine of omega t plus theta. Okay, any problem with that? If I just apply this formula, plug this in there, take the real part, I get this. And then if I find Vt now, I will plug this back into there and take its real part, I will get I over omega c cosine of omega t plus what now? What are the phases that I have to put in here? If this phase gives rise to this function, what would this phase give rise to in terms of this function? Yes, Ramesh?
Theta minus pi.
Very good. Theta minus pi over 2. Okay? But what is cos of something minus pi over 2? Sine of something, right? So this just becomes omega c sine of omega t plus theta. So you can see that the two functions, the current and the voltage, are 90 degrees out of phase, as you have expected, because the current and voltage through a capacitor is 90 degrees out of phase with respect to each other. Okay? So, what happens in the case that we have a resistor in series with the inductor and the capacitor? Say if we have this circuit instead, that we have a resistor and then I have L, I have C over here. What actually happens at resonance at the series impedance of this? If I call this Z for this part over here, Z actually is equal to j omega L plus 1 over j omega C. And this is equal to, if I were to write it out properly, 1 over j omega minus omega squared, okay, L plus 1 over C, and if I take the C out, then it is actually equal to this, minus omega squared LC plus 1. So right at resonance, what happens to Z? Right at resonance, if omega equals to 1 over square root of LC resonance, what would that happen? What would that become? What would this value become? Yes? Not 1. 0. It becomes 0. That's very important. Okay? This is 0 at omega equal to omega naught. Okay? So what happens is that at resonance, these two impedances cancel each other. You remember that one is positive, imaginary. This is negative, imaginary. This can be written as minus j over omega c. So it's negative imaginary, positive imaginary. If you pick the appropriate frequency, these two terms can cancel each other. And then what you have then is that this actually becomes just this circuit, with these two things cancel each other. And hence, at resonance, a series inductor together with a capacitor form a short circuit. Okay, in series they form a short circuit. There's something that you have to remember. What about when they're in parallel? When an inductor is in parallel with a capacitor, what happens? Let's say if you have this circuit over here. Maybe you just use the example of the book. We have an inductor okay, and then we have this impedance that acts in parallel, and if you don't like to work with impedances, you can work with admittances. Y must be the sum of the admittances of the three things. The admittances of this is 1 over R. The admittance of the inductor is 1 over j omega L. And then the admittance of the capacitor is just j omega c. Okay, I'm just adding the admittance of the resistor, the admittance of the inductor, the admittance of the capacitor. Okay, and this will be the admittance that you see from here. Okay, what happens if omega equals to omega naught for this thing? If omega equals omega naught, you see that these two terms will cancel each other. Just like that, these two terms would cancel each other. Okay, when omega equals omega naught, you can convince yourself of that quite easily. And you can pull out 1 over j omega L, and what you have left behind will be omega squared LC. I can pull out this 1 over j omega c from both terms. The first term will become 1. The second term, because I pull this thing out, I have to multiply by j omega L. This term multiplies by j omega L gives me minus square omega LC. And if you pick omega to be omega naught, what happens to these two terms? Cancel each other. So what you know then is that if you have an inductor and a capacitor connected in parallel, right at the resonance, these two terms cancel each other. So it has a total admittance of 0. If they have a total admittance of 0, what does that mean? It becomes an open circuit. That's right. Very good. Okay, that part becomes an open circuit. So what happens is that this has 0 admittance or infinite impedance. Is what it means. 0 admittance means z equals to infinity. Okay, because you get impedances and admittances just by reciprocating each other. This part will become infinite. So the equivalent circuit will be just this. Okay? At resonance. This is at omega equal to omega naught. At omega equal to omega naught. Okay? Omega equal to omega naught, these two terms will cancel each other. Then there's another question that you have to be very careful about, which is the issue of the resonance of this total circuit. If I were to look at the input impedance of this total circuit, that input impedance Z for the series connection is equal to R plus j omega L plus 1 over j omega C. So if you look at this equation again, you say that this has to be equal to the voltage of some sort. And if I short circuit this thing and write it as such, and set this to 0, does this have a resonance? Does this have a resonance? Well, according to the textbook, it says that when omega is real, this equation cannot be satisfied. That is, you cannot have this going to 0. Okay, this can never be 0 because if omega is real, this part is pure imaginary, this part is pure real. Okay? So Zs is not equal to 0 if omega is real. So if you are operating with real frequencies, that resonance is not possible. However, if you allow yourself to have complex omega, allow omega to be a complex number, you can actually get this to be 0. Okay? There are frequencies for which this would be 0 if omega is complex. Okay? Something that you will learn later on. That complex omega is actually the true resonant frequency of this structure. Okay? It's something that you will learn later on. So it's not completely correct to say that this thing has no resonance. It has resonances at complex frequencies due to the laws of the system. Okay? And similarly, if you were to hook this up and connect it to connect in such a way if you were to ask yourself if this structure, does this have a resonance? Okay, does this have a resonance? It also turns out that this would have a resonance if you allow omega to be complex. If omega is real, no resonance. Okay? If omega is complex, then it is possible that you can actually have a resonance for which y is equal to 0. Y omega is equal to 1 over r plus j omega L plus 1 over j omega C. Okay? Y omega is equal to 0 if omega is complex. And this can also be regarded as a resonance solution. This is also a kind of resonance solution, but I just don't want you to get confused that making the statement that this thing has no resonant frequencies. Later on in the course, you will learn that this thing actually has resonant frequency of the complex nature. Okay? It only has no resonances if you consider omega to be real. So, let's do example 4.25 of the textbook. And this textbook gives a ordinary circuit, but I just write down the phasor circuit. Okay? Without having to write down the original circuit. The original circuit is dt equal to cos of omega t. Okay? So in a phasor circuit, you will have a plus or minus of 1 volt here. And then you have a resistor, an inductor, giving an impedance of j omega L, and a capacitor giving an impedance of 1 over j omega C. Okay? You're asked to find the current and the voltage across the capacitor and the inductor. Okay, find the current and voltage across the capacitor and inductor at resonances. Okay, at resonances. At resonances, when they refer to is actually the resonance of these two pieces of elements over here. Okay, at resonance, then two pieces of elements, the inductor and the capacitor, will have their impedances cancel each other. We just learned that, which means that at resonance, this thing is just equivalent to a resistor network. Okay? And what is the current I? I would be equal to 1 over R amps at omega equal to omega naught. Okay? That is only true at omega equals omega naught, because otherwise these two pieces would not cancel each other. Okay? And then the voltage across the inductor, VL, will be equal to I times J omega L. This is what we learned from phasor circuit, will be the current times the impedance. And then if you work this out, the frequency should be omega naught. Okay? And then I should be 1 over R, so this is 1 over R J omega naught. Omega naught is equal to 1 over square root of LC. Okay, we just learned omega naught, we erase on the board. Omega naught equals to 1 over square root of LC from what we have learned earlier. And then multiply by L over here. So you get J times 1 over R times square root of L over C. Okay? And if you're given that V, originally V, is equal to that over there. So what is VL? Okay? If V equals that, what is the phase of I with respect to V? Is I out of phase or in phase with V? In phase, right? Because these two cancels each other. I is exactly in phase with the voltage source 1 volt. Okay? So I is not out of phase. So when you look at this quantity here, it is going to be how many degrees out of phase with respect to this? If you multiply this whole thing by J, okay, it will become minus sign, right? So what you have is actually minus 1 over R square root of LC sine of omega t is what you get for this this whole piece over here. The voltage drop across the inductor would be just equal to that. Okay? And then you can calculate the voltage drop across the capacitor in a very similar manner. And you just multiply the current I, multiply that by the impedance of the inductor, and you get the voltage drop across this inductor quite easily. Okay? And then you will find that at resonance, these two voltages cancel each other. Okay, because this becomes a short circuit. These two voltages cancel each other, and DC is minus BL at resonance. Okay? You'll find this to be a fact. And I can work out the detail for you. If you want to, I can actually work out BC. Okay? BC is equal to 1 over J omega C times I, just like I said before. You multiply by the current by the impedance, and you pick the frequency to be the resonance frequency. And if you work this out properly, I is 1 over R. Okay? And then omega naught is 1 over square root of LC. You have a C there. You have 1 over R there. And finally, you have minus J square root of L over C times 1 over R. That is your VC. Okay, you notice that your VC is just the negative of VR. Okay? The negative of VL, I'm sorry. That this quantity is just the negative of this quantity, which is what I referred to over there. Okay? And then you can plot out your voltages. You plot out your voltages, and much to your surprise, you find that in the time domain, the voltage can be actually larger than the input voltage. Okay? So you can convert all these quantities back to the time domain. This quantity as well is this is actually I have already converted this back to the time domain, so I shouldn't say equal. I should say that if this quantity is converted back to the time domain, it should give you that quantity over there. And if I were to convert this quantity back to the time domain, I should get 1 over R square root of LC sine of omega t. Okay, if I were to convert this quantity back to the time domain, this is what you get. And you know what the rule is? The rule is actually take this VC and multiply by e to the j omega t. Okay, and take its real part. And when you take its real part, you will get the quantity over there. Okay? And this actually is VL in the time domain. It's not equal to that phasor quantity actually. I shouldn't say that. And you can plot these quantities out. And you find that when R is very small, these quantities can be quite large. Okay? In the limit when R goes to 0, what happens to them? They go to infinity. Why is that so? Why is that? In the limit when you have very small resistor, I just drive this system with a finite voltage source. Okay? I find that the current that sloshes back and forth in this circuit can go to infinity, creating voltages that are very large. Okay? The current is actually not going to infinity, it's the voltage that are going to infinity. The current I is limited by this resistor. Okay? The current I is limited by this value, but the voltages that happens between them can go to infinity. Why is that so? Yes?
There's nothing to dissipate the energy.
Nothing to dissipate the energy, that's a good thing. Okay? Name is Aaron Smith, right?
Yes.
Okay. And then that's a good reason. There's nothing to dissipate the energy. What is another reason?
Look, I was saying after going back and forth with the energy in the system and when each other send current, then when they're opposing, it becomes a different. So that's
Right. What happens is that if you have something resonating, it is a self-sustaining system, even without a driving source. Okay, it sustains itself even if you don't have to put any driving source. So if I had no driving source, if the resistor had not been there, if I just drive this system with 0 voltage, it will have a current flowing there. Okay, it will have a current flowing there. But now if I were to drive this system with its resonant frequency, okay, what happens to its amplitude? Like you do in a park. If you know how to pump a swing in the park, if you pump it at the right frequency, your swing will become larger and larger, right? Have you played that in the park? When you were young, right? When you were young, when you're in the park, you know how to pump the swing and give it an impulse of energy right at the right frequency, the swing becomes larger and larger. So the same thing is happening here. If the resistor is very small, Okay? And you pump this system with the voltage right at the resonant frequency. There's going to be more and more voltages building up in this system. Very much like what happens to the swing in the park if you were to pump it with some energy. Yes?
I just have a quick question. How do you go from the phasor to the time domain again?
Okay, let me go through that. Okay? You know how I can convert this circuit to a phasor circuit, right? No problem with that. I know how to find the current. I find the current by assuming that these two impedances cancel each other at resonance. That happens at resonance. Then the I is just 1 over R. Then if I find the current through this system, I is going through this system, okay? It's going to cause a voltage drop at the inductor, and that voltage drop is I times this. And then I know what my omega naught is. I have written it down somewhere in the blackboard over here. I rewrote it again over here. Okay, I plug it in, I get this thing. I know what my R is, I plug it in. I get this quantity. This is completely in the phasor world. And in order to get V of t, the inductor, I take the real part of V of L in the phasor world and use this formula. This formula you have to commit to memory. Okay, we derive this formula, you have to commit to memory. And then if you were to put this in, V of L being equal to that, so it will be real of 1 over R. Let me erase this. Times square root of LC times J. And what happens if I express J in terms of a polar form? Is e to the, what is this J in polar form? J pi over 2, right? And then I put this back in there. J omega t. Okay? And now if I take the real part of this quantity, I will have 1 over R square root of LC cosine of omega t plus pi over 2.